Hi, everybody. In these last set of videos, we're going to focus on applications. So we're going to look at applications that have to deal with exponential growth and decay, and then also some other examples with modeling data. So here you have your two main graphs for your exponentials. Here you have the increasing version and the decreasing version. And these have been edited just to represent more the growth and decay models. So typically we're letting our x-axis be time here, things like population growing over time, for instance. So we're excluding the negative values, which makes sense for most applications. So that's why you do see that distinction here and that change. So over here you have that initial starting point at a sub 0, and then here you have your initial starting point of a sub 0. So this is your general format for exponential growth or decay. And if k is greater than 0, the function models the amount or size of a growing entity. So again, often things like population growth, for instance, if the population is growing, it typically grows exponentially a lot of times. A sub 0 is the original amount or that starting size of the growing entity at time t equals 0. A is the amount at time t, so maybe you're looking at what happens after 2 years or 5 minutes, whatever the time is. And k is a constant that represents the growth rate. So that's really important here. That k value is that growth rate. Now, if k is less than 0, then you have a decreasing or decaying model. So let's say your population is decreasing over time, something like that. A sub 0 is still the original amount or size of the decaying entity at time t equals 0. And then A is the amount at whatever time t you're looking at. Maybe you're looking at t equals 5 years. And k is that constant representing, in this case, that decay rate. Now, remember, rate is another way to think of a percent. So we often use that word rate to represent the percent, particularly in decimal form. So that's going to help us out later as well. And these are your two basic graphs. So let's look at an example. I'm going to look at the graph in figure 4.22, which is on page 522 in your text. And I'll just show it to you here on the video, but you can look at it on your own at home. And it's just a bar graph here. So it represents the US population for 6 selected years, starting at 1970 through 2020. And the population is given in millions. So in 1970, the population was 203.3 million people. And then in 2020, the population was 331 million people. Okay, so we're going to use this information here in our problem. So we're going to find an exponential growth function that models the data. If you look at the data here, I guess I should bring the graph back. It's a little hard to see because we only have 6 points. But if you start looking at the change in the data, you do see sort of this increasing idea. So in the beginning here, the change is about maybe 23 million. And then at the end here, you're changing by a little bit more than that. So you're going, so let's see, 308.7 to 331 million. So actually maybe 21 million, so not more. But the change here does look a little bit more like it could be a curve. So they want us to use that exponential growth here to model it. Now, I think if we had more data on this end, you would be able to see that curve a lot more clearly. And you would see that, the model for population is a little bit more of a curve, not necessarily linear. But one thing we're going to talk about later on in the videos is how do you determine if you should use an exponential, if you should use a linear. So we actually have a more rigorous process for determining that, which we'll talk about later. So here our book wants to use an exponential growth function to model the data. And then we're going to learn how to set that up. So first of all, you want to know that we're doing a growth function, right? Because that population is increasing. So I'm going to start with my basic function information here. You can use f of t, or I'm just going to use a. So a equals a sub 0 e to the k t. And we want to model the data for 1970 through 2020. So our starting year is this 1970. So this is going to relate to our time being 0. And we do this a lot. So remember that we often have a starting year because we don't really want to go back to year 0. So here, t equals 0 is going to relate to 1970 in this case. So our starting population in 1970 is going to give us our A sub 0, and that was 203.3 million people. So remember, your A sub 0 is that starting value, whatever the value is at time 0. So that's your starting point. Now, the other thing we often have to find out in our formula is this K value. Everything else will be fine. So we leave the A, we leave the T. Those are our two main variables. E is a number, but we do need to find out that growth rate, that K. So how we do that is we plug in another point and we solve for K. So here for part A, the other value that I know that our answer is really focusing on here is that in 2020, the population was 331.0 million. So we have a pair of data here. Now our X value in this case, remember we're starting in 1970. So we have 50 years have gone by in this case. And then so I guess we're going to use, I'm using X, but we should use T, I guess, here. And then our A value would be that 331. That would be like our Y. So I'm going to plug in this pair of data. And then what I'm going to do is I'm going to solve. Oops, sorry, guys. It should be K times 50. I'm going to solve for K. So here I just plugged in 50 for T. I apologize, I was writing that backwards there. So I plug in 50 for T, and then I'm solving for K. Now think about this, when you have an exponential by itself, you do want to try to get the exponential alone first. So I'm going to go ahead and divide by 203.3 to start. So I have e to the 50k is equal to 331 divided by 203.3. I'm going to leave it in the fraction form for now because I do want my answer to be as accurate as possible. And now the exponentials by itself. So think about what other strategies we've learned. When we're kind of getting stuck, we often take the natural log of both sides, and we're going to use that strategy here. Remember, when we take the natural log, what happens is this 50k is going to come out and be multiplied, and then natural log of e is just 1. So it basically sort of cancels itself out. We just have a multiplier by 1 here, so we don't need to write that in. And what I have left is the natural log of 331 over 203.3 is equal to just 50k. Now remember that they cancel because they have the same base, which is really important. So natural log in e, the natural log of e is 1. So you get that multiplier by 1 here. If you had a different base, then you would have to write that in. It's only because they have the same base that you get that canceling effect. And now I can solve for k by dividing by 50. So that's the exact value. And then what you could do is you could use your calculator here to find out what k is. So I'm going to take out my calculator. So I'm going to start by doing the natural log first. I'm going to do natural log. And then notice how it's just one natural log with the division. So 331 divided by 203.3. And then I'll close my parentheses. So it looks like this. I just have one. See if we can see that. One natural log there. And then I'm going to divide that by 50. Brighten that up a little bit. And then what we get for our value is about 0.009748731. Now, I'll tell you that the more decimal places you use, the more accurate this is going to be. I would normally recommend probably at least 4 or 5 decimal places here, if I'm being honest. Your book only uses 2 decimal places, so I'm going to defer to what your book's doing just to stay in line with this example. But again, the more decimal places you use, the more accurate it's going to be. So in general for K, I would recommend many more decimal places than just 2. I'd probably recommend at least 4 or 5 there. So I'm going to use just 2 because that's what your book does. But realistically, I'd probably want you to use more if you're actually doing this in the real world. So your last step is to just fill back in. So go back to your equation, which was here. Fill in that k value. Again, we're going to round, so it's about 0.01. And now we have a working equation here that models this data. So let's answer part B. By what year will the US population reach 400 million? So we want to know the year, meaning we're looking for time here. And we know that the A value is 400. So I can use my formula. So I have 400 is equal to 203.3 e to the 0.01 t. I'm going to start by dividing 203.3 on both sides. So I have 400 over 203.3 equals e to the 0.01 t. Now I'm using very similar solving technique here. I'm going to take the natural log of both sides. And just like before, that exponent is going to come out front, and the natural log of e is just 1. So we're multiplying by 1 there, which is not going to change our value. Final step is to divide both sides by 0.01. And I'll let you guys try this part at home, but if you round to the nearest year, you get about 68 years. Now remember that our starting year was 1970. So you want to take that 1970 and add 68 to it. So we're estimating that around the year 2038, the population would be 400 million. Now remember, this is just an estimation. And we want to keep in mind that we're going out to 2038, which is pretty far beyond the scope of our data here, right? Our last data point was 2020. So you should definitely take this information with a grain of salt because it's a pretty far away prediction, I think. So things could definitely change in the next, well, let's say we go from 2020 in the next 18 years, right? A lot of things could change. But it gives us an estimation of what to expect, assuming that things stay on the same path. Now, another thing I will note here is that we created the equation using only 2 points. We had the initial starting point, and then we used the ending point here. So you need a second point. So this strategy only relies on 2 points to create the model. So you want to keep that in mind as well. It's not going to be the best model. It's okay. It's a good starting model here to model that data. But using more points and more data would actually give us a better model. To use more points, you would want to use technology. So we'll talk about that a little bit in the videos. I'm not going to make you do the technology on your own, but you would need like a TI-83 or 84 calculator or some other kind of higher level functioning utility that would do that for you. So there are other ways to get this formula or this model that would be a little bit more accurate using technology that takes in more than just 2 data points. It takes in all the data points that you have and creates the best model around that. All right, let's do another application here. So our next application has to do with carbon-14 dating. Carbon-14 dating is used to determine the age of some fossils and artifacts. It's based on considering the percentage of carbon-14 remaining in the fossil or artifact. So basically what happens is all living things have carbon in them. And what happens when a living organism dies, it stops producing and taking in carbon-14. I'm not a scientist, that's kind of basically what happens is you stop producing that carbon-14 in the body. So what we can do is we can compare how much carbon-12 is to how much carbon-14 is left because they start with the same amount at death and look at that ratio. So it allows scientists to determine how much carbon-14 has been lost since the death, and then we can use that information and some mathematics to actually determine the year. So I do encourage you, if you find it interesting, to read more about it. And it uses the idea that carbon-14 decays exponentially with a half-life of about 5,715 years. So the half-life of a substance is the time required for half the sample to disintegrate, right? So let's say that at death, you have 100% of carbon-14 in the body that would have originally been there. Then after 5,715 years, you only have 50% left. Then after another 5,715 years, do we have 25% left, right? So you cut that amount in half every time 5,715 years passes. So we use this idea and exponentials to actually date a lot of items. And it's useful for fossils up to, your book says 80,000 years old. Some of the websites I've seen online say more like 50,000 years old, because after that time, there's not enough carbon-14 left to accurately determine the age. There's very little left. So they'll use another radioactive isotope instead to date the item. So there are other substances in the body that have longer half-lives than just 5,000 years. So they use a different isotope instead to date things that are older than just, let's say, 50 to 80,000 years. So it's a similar process. All right, so let's use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. So I'm looking at decay here, right? So that amount is decreasing. So I'm going to start with my general formula, this one right here. And just remember that you're decreasing, so your K is going to end up being negative in this case. All right. Now, I don't have an exact starting amount here, and actually the initial amount of carbon can change from organism to organism. So what you would do is you would look at how much carbon-14 and carbon-12 are in an organism that's alive for that particular species, and then you could then look at how much is left in the fossil or the artifact that you have found. Plants have carbon-14 also, so similar idea works if you have a plant item, not just actual, like an animal or things like that. All right, so here's our starting setup here. And then what you want to think here is that what's happening is that after 5,715 years, you have half the amount left. So if your starting amount is A sub 0, then after 5,714 years, you have half left. So what's half of A sub 0? It's just 1/2 of A sub 0 or A sub 0 over 2. So it doesn't matter what that starting amount is, it's still going to be divided by 2, whatever that starting amount is. So your formula looks like A sub 0 over 2 is equal to A sub 0 e to the kt. And actually, in this time here, we're going to fill in the t as well, because we do know the t in this case is going to be that 5,715. So this is for carbon-14. Again, different items or different elements have different half-lives. So this is the carbon-14 half-life. All right, so now I do want to solve to get that K. So what's going to happen here, this A sub 0 is kind of weird looking, but you can actually still divide both sides by A sub 0 to cancel it out. And it cancels here and it cancels here. And then what you actually have left is just that half is equal to e to the 5,715k. And again, this half becomes that because you have half the amount left. Now we're going to solve. So I can take that natural log of both sides. So I have the natural log of 1/2 equals 5,715k. And again, natural log of e is 1. So I'm just going to end up multiplying by 1 there. And then I'm going to divide both sides by 5,715. So our k value is the natural log of 1/2 over 5,715. Now your book here uses the following for the decimal. So they rounded to 6 decimal places here, so we'll stick with that. And try this at home. Plug this into your calculator and make sure you're getting the same value. So in our decay model, then our k value is going to be this. So our final model will be A equals A sub 0 e to the negative 0.000121 t. Now, again, I'm using A sub 0 here because I don't necessarily know the starting amount. Usually we think of it as a percent a lot of times in these examples, but each organism has different starting amounts depending on the species and things. So I don't have a one general starting amount for every single species. All right, so let's look at part B here. In 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab herdsman. Analysis indicates that the scrolls wrapping contained 76% of their original carbon-14. Estimate the age of the sea scrolls. So here we're given a percent of the amount that was left rather than a starting amount and an ending amount. So when you have a percent, what you're going to do is set it up like this. So our ending amount here, it's not half, it's going to be 70, what do we say, 6%. So I'd write it as 0.76 times that a sub 0. So this is 76% of whatever the original amount was. And then now when I solve, again, I don't even need to know the original amount to do the math. I just need to know the percent that's left. And again, that percent that's left is found comparing carbon-12 in the body to carbon-14 in the body. Because what happens is when an organism dies, they're the same amount in the body. The ratio is equal. So when the organism dies, carbon-14 started, carbon-12 does not. So they're able to compare that ratio to see how much carbon-14 was lost. But again, I kind of giving you just kind of the quick idea here, but you can look more into it. It's actually really interesting to think about how they date some of these fossils. Ln and E are going to just give me a value of 1, so it's going to cancel out in this case. Take that natural log of both sides and divide. All right, and again, you can try the calculator part at home. You should get rounded to the nearest year about 2,268. So think about this. So our scrolls, so the Dead Sea Scrolls, right today, Dead Sea Scrolls are approximately 2,268 years old, plus the number of years between 1947 and now. So that little piece there is because this was found back in 1947. So this calculation would have been analyzed back in 1947, we'll say. So at the time, we had approximately 2,268 years. So if we want to make that a little bit more accurate, nowadays we're adding what, about 60 years, a little over. So we would add another 60 years to this. So it's over 2,300 years old at this point, approximately.